Salam and peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase, a cyclic rhythm defined at every point in the universe. Its first derivatives give three simultaneous echoes: time, which we call omega, space, which we call k, and motion, which we call v, built from both omega and k. Above them, higher derivatives form a branching tree that goes on forever. Every law of nature is a pattern in this tree of derivatives of phi. Today, we zoom into just one branch of that tree. In the last part, we sat with phi itself, the silent page of the universe. We saw that nothing visible happens until phi begins to change, and that every derivative is really just a more detailed question about this one underlying rhythm. Now, we take our first real step up the temporal branch of the master tree. We climb from the root, phi, to its first temporal echo, omega, the local tempo of reality at each point. Think of this path as walking up to a vast city of rhythms. Every street corner, every room, every atom, every star has its own ticking, its own inner beat. Omega is the quantity that tells us how fast those beats are turning. It is our first clear temporal letter in the holophase language. Linguistic role. Omega is the basic temporal letter. Inside the holophase language, omega is a core letter. If phi is the silent page and the underlying ink, omega is the first stroke that becomes legible in time. If you imagine the master tree like a great dictionary, then the root entry is phi. The first temporal entry just above it is omega. Omega answers the simplest possible time question about phi. At this point in space, how fast is phi turning right now? It does not yet care about curvature, acceleration, or higher refinements. It is the plain tick rate of the underlying cycle. So in linguistic terms, omega is a primary consonant of the temporal tower. Every higher temporal nuance, acceleration of the tick, jerk of the tick, complex modulations, is built on top of omega. Without omega, the temporal tower has nothing to stand on. If phi is the page and the possibility of writing, omega is the first clear sound, the basic ta-ta-ta, that tells you there is a rhythm at all. 2. Scientific essence, what omega really is. Now, let us translate that into operational language that a physicist or mathematician would recognize, but without symbols on a screen. Omega is, very simply, the rate at which phase advances in time at a given point in space. Imagine you have a little clock hand representing phi at some location. As time passes, that hand rotates around the circle. Omega tells you how many turns, or what fraction of a turn, it makes per unit time. In more concrete terms, for a vibrating guitar string, omega is the pitch of the note. Higher omega, higher pitch. For light from an atom, omega is the color. Red light has a lower omega than blue light. For a laser, omega is the central frequency around which the field oscillates. But in the holophase picture, we do not treat omega as frequency of some separate wave. We treat omega as the first temporal derivative of phi, the first measure of how phi's phase is changing in time. It is the local tempo of the holophase at that point. Operationally, how do we see omega? We measure oscillations, how often something repeats per second. We look at spectra, lines or peaks that tell us certain omega values are present. We follow repeated cycles, the beating of a signal, the rhythm of a field. Everything that has a repeated pattern in time, a wave, a vibration, a rotation, is, in this language, exhibiting a particular omega. It is phi speaking in a very regular temporal accent. If you want to see the full mathematical derivations and the precise equations that connect phi and omega, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Here, we are focusing on understanding omega through images, stories, and physical intuition. 3. Dimensional expression. Omega in time, space, and motion. By our core rule, every structure in this language must have three echoes: in time, in space, and in motion. Omega is the temporal letter of the first tower, but it still has spatial and kinematic shadows. In time, omega as local ticking. In time, omega is straightforward. It is the tick rate. Imagine placing a tiny metronome at each point in space. At some points, it ticks slowly. At other points, it ticks very fast. Each one keeps track of where phi is in its cycle, and omega is how fast the metronome is ticking there. So omega's temporal meaning is how quickly the local phase of phi is advancing, how dense the cycles are in time. More cycles per second means larger omega. When we measure the pitch of a sound, the color of light, the clock rate of an atomic transition, we are measuring omega, the time echo of phi. In space, omega as temporal coloring of patterns. Spatially, omega shows up as a coloring of space with different rhythms. Imagine a large surface where at every point there is a little flashing light. Some regions flash quickly, others flash slowly. If you could look at this surface from above, you would see a pattern, not of height or texture, but of tempo. In reality, different places in a medium can host waves with different omegas. In curved spacetime, like near a massive object, the effective ticking rates of local clocks can differ. Even if we do not write the equations, we can still understand this qualitatively as a variation of omega in space. So omega's spatial echo is a map of how fast time flows for the wave-like processes at different points. A field of local tick rates that can change from place to place. We infer this spatial distribution of omegas through experiments. Spectral lines shifting in different regions. Frequency patterns changing as we move across a material. Pulses speeding up or slowing down as they traverse different zones. In motion, omega tied to how patterns propagate. In motion, omega ties directly into how patterns travel. A wave that oscillates faster in time, higher omega, but has the same spacing in space, same k, will typically have a different propagation speed. In many systems, the relationship between omega and k, the dispersion relation, determines the group velocity, the speed at which wave packets, and therefore information, move. So omega's kinematic echo is: it sets part of the rule that determines how fast disturbances move. Combined with k, it tells us the velocity of energy and information flow. In the holophase language, omega is the temporal letter. K is the spatial letter. The way omega depends on k is a grammar rule, a syntax relation, that determines motion, v. If puzzles arise, if, for instance, we measure omega and k in a system, and the resulting motion does not match what the holophase grammar predicts, then our understanding of omega's role must be revised. That is where falsifiability comes in, and we will return to it shortly. Position of omega on the master tree. Let us place omega precisely on the master tree. At the root is phi. Just above it, along the temporal trunk, sits omega. It is a first-order derivative, the first layer of temporal difference. The base of the temporal tower. Above omega, we build alpha, the change of omega, jerk, snap, and other higher temporal derivatives. We can visualize it like this in your mind. At the very bottom, a simple circle at each point, the possible phase of phi. Just above, arrows along the time direction that say, here, the phase grows at this rate. Those arrows are omega. Everything else in the temporal tower, second, third, fourth derivatives, is basically asking, how is omega itself changing? This means omega is the gateway to temporal nuance. If omega is constant in time at a point, the local rhythm is steady. If omega varies in time, we can describe that variation with alpha and higher derivatives. Without omega, there is no temporal structure at all. With omega alone, we can already describe a very rich class of behaviors: pure tones, constant frequency waves, steady periodic oscillations. 5. Interactions with neighboring branches. Omega does not live alone. It is tightly coupled to K, d phi, V, and the second-order structures above it. Maggie and K. Rhythm and spacing. The most important relationship at first order is between omega, the temporal rate of change of phi, K, the spatial rate of change of phi. Together, these two form the basic descriptors of a simple wave. Omega tells you how rapidly the phase moves in time. K tells you how rapidly the phase moves in space. The relation between omega and K, how one changes when you change the other, is the dispersion relation. It is like a grammar rule that says, given this spatial pattern, here is how fast it must oscillate in time to be allowed in this medium. If you keep omega fixed but change K, you change the wavelength and therefore the shape of the pattern in space. If you keep K fixed but change omega, you change the pitch, the color, or the temporal rhythm. Omega and d phi, the unified change. We also have omega as part of the unified change d phi, where time and space are mixed. When you move in both time and space at once, for example, following the crest of a wave as it travels, the total change of phi you feel along that path is built from a combination of omega and K. Omega tells you the change from the time component of your motion. K tells you the change from the spatial component. The requirement that d phi can be zero along some trajectories, meaning phi does not change along those paths, is what picks out the spatial velocities v. Those velocities depend on omega, so omega directly shapes which motions are allowed if we want to surf a phase crest. Omega and higher temporal derivatives. Above omega, we find alpha and higher temporal derivatives. Alpha tells us whether the local ticking is speeding up or slowing down. Higher derivatives tell us the nuance of that change. These structures influence phenomena like frequency chirps in pulses, the onset of instabilities where oscillations become more complex, the detailed shape of time-dependent processes. So omega is the baseline on which all temporal modulation rides. 6. Semantic meaning. What kind of meaning omega carries? What kind of meaning does omega carry for the universe? Omega is the meaning of tempo. It tells the universe, at this point, this is how fast you are cycling. When we say meaning here, we do not mean human meaning, but structural meaning. What kind of role this quantity plays in shaping patterns? Omega's semantic roles include setting the pace of processes. Fast omega means rapid oscillations, short cycles, quick repetition. Slow omega means gentle, long cycles, slow repetition. Defining temporal identity. Systems can be recognized by their characteristic omegas, the specific frequencies they prefer to oscillate at. An atom has certain omega values it will emit or absorb. A musical instrument has characteristic resonant omegas. Structuring time patterns. Omega is the base rhythm on which more complex timing patterns are built. Beats, envelopes, modulations, and interference in time. In all of these roles, omega is not just a dry parameter. It is the temporal accent of the holophase at each location. It says, this is how quickly the invisible metronome is ticking here. 7. Stability, variability, and falsifiability for omega. How does omega behave across systems, and how can we test the holophase picture of it? Stability. Omega is often extremely stable in real systems. Atomic clocks maintain extremely precise omegas for long periods. Laser cavities lock into sharp omegas corresponding to allowed modes. Many physical systems have well-defined resonant omegas. This stability is exactly what allows us to treat omega as a meaningful, measurable letter in the language. When a system has a characteristic omega, that is like a stable sound in its pronunciation. Variability. At the same time, omega can vary. Across space, different regions can have different frequencies. Over time, signals can chirp, speeds can change, beats can appear and disappear. Across systems, different media and structures favor different sets of omega values. From the holophase perspective, these variations are not arbitrary. They are restricted by the derivative relations of phi and by the dispersion grammars that link omega to k. Falsifiability. Now the crucial question. How can this picture be wrong? The holophase claim about omega is 1. Omega is the time derivative of a single underlying phase field, phi. 2. Its values are not independent. They are tied to spatial derivatives, k, and motion, v, through structural relations. 3. These relations are universal. They can be written in the same language across different physical systems. We can test this claim in several ways. Measure dispersion. For waves in different media, light in a crystal, sound in air, water waves, we measure the frequencies, omegas, and wavelengths related to k. We then see whether their relationships can be written as different manifestations of a common underlying derivative grammar, rather than completely unrelated coincidences. Check consistency with motion. Given a measured relation between omega and k, the holophase picture predicts certain group velocities v for wave packets. We can test whether those velocities match observed propagation speeds. If they do not, and no refinement of the derivative structure can fix the discrepancy, the holophase grammar would be in trouble. Look for breakdowns. In extreme conditions, very high energies, very small scales, very strong fields, we can look for situations where the usual relationships between omega, k, and v break down. If those breakdowns cannot be interpreted as higher order corrections within the same phase language, but instead point to genuinely different kinds of structure, the holophase model would need revision. Again, the detailed design of such experiments and the precise formula used to test them are laid out in the formal holophase papers on Zenodo. Here, we keep the big picture. Omega must play by universal rules if the language claim is to hold. 8. Where omega appears in nature. Omega is everywhere in physics. Whenever something oscillates, there is an omega. The alternating electric field in a radio wave has a particular omega. The vibration of a crystal lattice has phonon modes with characteristic omegas. The orbit of a planet around a star has an angular omega. How many orbits per unit time? Even when we do not talk explicitly about phase, any periodic behavior can be rephrased in the language of omega and phi. Heartbeats, breathing rhythms, brain waves in neuroscience all have repeated patterns with well-defined omegas. Mechanical systems, like a mass on a spring, oscillate with an omega that depends on mass and stiffness. In each of these cases, the holophase view says, there is an underlying phi whose temporal derivative at that location is exactly the omega we measure. Different systems correspond to different branches of the derivative tree, but the concept of omega is the same across all of them. The strength of this view lies in its unity. We no longer have one idea of frequency in optics, another in mechanics, another in quantum physics. We have one letter, omega, whose role is always how fast phi is turning in time, no matter which branch of reality we are looking at. 9. Everyday analogies. Feeling omega in daily life. Let us make omega extremely concrete with simple everyday analogies. Music. Tempo of a song. When you listen to a song, you can tap your foot to its beat. That beat is a direct, felt experience of a certain omega. A slow, calm song has a low omega. The rhythm is sparse, the cycles are long. A fast, energetic song has a high omega. The beat comes quickly, cycles are short. If the song speeds up or slows down, the omega changes. You can feel that immediately, even if you never think the word frequency. In holophase language, the song's beat is a macroscopic manifestation of an underlying omega structure in sound waves and in the nervous system. Omega is the how fast of the repeating pattern. A ticking clock. Stand next to an old mechanical clock. Tick, tick, tick. Each tick represents a cycle of some internal mechanism. The rate of those ticks is a very concrete omega. Now imagine a room full of clocks, each running at a slightly different speed. That is like a field of omega values in space. Different local tempos, different tick rates. Walking and heartbeats. Walk up a hill quickly and feel your heartbeat. As you speed up, your heart's omega increases. As you rest, it slows down. What you are feeling is not just a metaphor. It is a real oscillatory process in your body with a real frequency. Omega is the letter that names this role. How many beats per minute, how many cycles of contraction and relaxation. Night and day. Even the cycle of day and night can be seen as an extremely slow omega. One rotation of the Earth per day. The sunrise, noon, sunset, night, repeat. That repeating pattern is, in a very broad sense, an omega acting on the entire planet. So omega is everywhere in your daily life. In music, clocks, heartbeats, breathing, walking, the rotation of the Earth. In all of these, it is the same structural idea, cycles per unit time. 10. How to read omega in the world. How can you, as a listener, practically recognize omega when you look at the world? Here is a simple checklist. 1. Find something that repeats. Look for any pattern that comes back again and again. A blinking light, a vibrating string, the hum of a machine, the beating of a heart. 2. Count the repeats in time. Ask, how many cycles happen in a second or in a minute? That count, cycles per unit time, is omega. 3. Notice differences between places. If the same kind of process has different speeds in different locations, like one star pulsating faster than another, or one machine spinning faster than another, then you are seeing a spatial distribution of omega values. 4. Look at how changes in omega affect motion. If a wave with higher omega but similar spatial structure travels differently, perhaps faster or with more energy, then you are seeing how omega participates in the motion grammar of that system. 5. Connect it back to phi. Imagine that behind the scenes, there is a local phase that turns with this omega. When you do that, you are starting to think in holophase language. In this way, you can train yourself to read omega as a basic letter of reality. The letter that says, this is how fast the cycle is turning here, in time. 11. Connection back to phi. Omega as phi's first audible voice. At the end of this part, let us return to the root. Phi itself is silent to direct observation. You never see an absolute phase. You only see differences and changes. Omega is phi's first audible voice in time. When phi turns steadily at a point, omega is the number that tells you how fast. When you hear a tone, see a periodic signal, or measure a spectral line, you are listening to phi speaking through omega. Omega is nothing other than phi's temporal derivative. But seeing it as a letter in a language helps us remember its structural role. Everything we have said here still fits into our core thesis. There is one field, phi, whose derivatives form an infinite language. Omega is the first temporal letter of that language. It carries the meaning of tempo. It lives simultaneously in time as a local ticking rate, in space as a map of different local rhythms, and in motion as part of the rule that decides how patterns travel. Its behavior is not arbitrary. It is tied to k, v, and higher derivatives by grammar-like relations. Those relations can be measured and tested. If the world refuses to match them, the holophase language must be revised. That is what makes this a scientific framework, not a mystical belief system. 12. Closing movement. Stepping firmly onto the temporal branch. As we close this part, picture the master tree once more. At the bottom, phi, the silent root. Just above it, along one main branch, sits omega, the first clear temporal letter. It is like the first drum beat in a piece of music, the first tick of a clock, the first heartbeat in a living body. By now, you should be able to feel omega as the tempo of reality at each point. Recognize it in everyday life whenever you encounter repetition in time. Understand that it is one of the core letters from which the universe writes its stories. In the next part, we will walk sideways along the tree, from the temporal branch to the spatial one, and meet K, the spatial meaning of phi. If omega tells us how fast does phi turn in time, K will tell us how quickly does phi twist across space. Together, omega and K will give us the first complete sense of how phi writes patterns across spacetime. You're now firmly standing on the temporal branch. Next, we learn how the same language paints shapes in space. Peace be upon you.